Hi everyone, thanks for coming. So today I'm going to talk about knowledge representation and reasoning with deep neural networks. This is work I did both at UMass and at Google Brain. So just to get things started, we want to represent world knowledge in some form so that computers can use it. And then by reasoning, I mean we want to manipulate this knowledge so that we can produce some desired behavior. So this is like really high-level definitions, and I think this has important implications in fields like language understanding and robotics. Okay, so I think really the first systems that come under this paradigm relied on symbolic representation, and reasoning was performed using some approximate search algorithm. And when I started writing my thesis, I was looking at the Wikipedia page to figure out the first systems, and I think at least Wikipedia says general problem solver is the first system that comes under this, and I think all these systems are like really carefully manually programmed for some task, and they're very precise, and I think the general problem solver was like developed for the towers of Hanoi problem, where the knowledge is like the permissible transformation, and the search algorithm helps you go from some initial state to the goal state. Okay, so these were like the classic knowledge representation and reasoning systems.
The general problem solving was a little bit more general.
Oh, a little bit more general. Sorry, yeah, I started reading about this like really classic work only 2 months back. Yeah. So anyway, so the focus of my work was like to do more kind of more applied stuff of like trying to reason on these tables. For example, this is a table from a random Wikipedia page, and you get an input natural language question, and you want a system that can perform reasoning on this given table to answer the question. So this means so if you think about what the system has to do. So given a question like which venue had the biggest turnout, it has to pick the column attendance, and if you notice, the word attendance does not occur in the question. So this is some kind of like symbol grounding that's challenging, and then it has to perform a discrete operation of getting the position of the maximum entry, and then it goes back and prints the corresponding entry from column side. Okay. So this basically can be simply described as trying to map the input question to a program, and then when you execute the program on the given table, you get the answer. Okay, and what I want you all to take away from this slide is that this involves manipulating symbols and discrete processing. Okay, and the early systems, the really old systems, are not really suitable for this for these kind of problems, right? So handling real-world data is challenging with these systems because they are manually programmed, and it's hard to cover all the corner cases. And it's also, when you have symbolic systems, it's hard to generalize to a large number of symbols because each symbol is treated independently, which means that covering all the symbols is again a challenge. And the very early systems had no learning component, which means that transferring when you move to a new task, you almost start from scratch. Okay, and this is just some recent work, that address one of the drawbacks, where some of the components are learned, but these systems are still symbolic, which means that a lot of the problems still remain. Okay, so I'm going to leave knowledge representation reasoning just for a minute to describe what was happening when I started my PhD thesis. Was deep neural networks were really taking off, and they were performing really well on perception tasks like speech and image recognition. So the input is some continuous vector, and you have many hidden layers of continuous processing, and you reach an output. Okay, and all these hidden layers are learned through gradient descent. And again, the key takeaway here is that the processing is done in continuous space. Okay, and just to highlight the differences between like what is involved in perception task and reasoning task. The input is continuous in perception tasks, whereas with these reasoning tasks, you have discrete symbols. And I think a bigger kind of like a bigger deviation is in the processing involved, where in perception task you basically require some kind of fuzzy or continuous processing, whereas in reasoning you want to induce programs similar to what I showed you in the beginning, and you also sometimes require to induce rules. Okay. And the focus of my PhD thesis was to like trying to bring these, I think, kind of like parallel research areas of neural networks and knowledge representation reasoning closer together. And that, I think, raises two big questions. So the first one is, can we represent symbols with distributed representations and learn them? And I think a bigger challenge is, can we learn neural networks to perform reasoning with these representations? Okay. And I think if we can develop systems that can do this, this gives us a lot of advantages. The first one is, the moment you start representing symbols with distributed representations, there's natural sharing of information between these symbols, which means that you can generalize to large number of symbols. So think about using word-to-vec vectors compared to using bag of words representation, right? Like you don't face the out of vocabulary issue as much, and these are, now we can start doing powerful reasoning since these are nonlinear models. And I think the most important advantage, I think, is that you can learn these models end to end just from data, and this means that handling real world data becomes easier. Okay, so to answer these questions, I'm going to cover two topics. The first one is to perform simple reasoning on a massive structured knowledge base, and the second part is to perform more sophisticated reasoning on semi-structured web tables. Okay, so task one is you're given a knowledge graph. So knowledge graph has entities like Melinda Gates and Gates Foundation, and then there are relations connecting them. And given this information, you want to infer missing links in the knowledge graph. So here, Melinda Gates is chair of Gates Foundation, and Gates Foundation is headquartered in Seattle. Now, using these two facts, it's highly likely that Melinda Gates lives in Seattle. Okay, and basically the model has to infer rules similar to what I've shown here. Okay, and task two is what I described before, which is you're given these semi-structured tables from Wikipedia, and then you're given natural language question, and the task is to map this question to a program. Okay. Yeah.
I think Melinda Gates is in Bellevue.
I'll correct it for my next talk. So before jumping to my work, I'll talk about related work in reasoning that happened in the last few years, which all basically used neural networks. And there's been work on natural language inference, visual question answering, reading comprehension, and many more. Okay, and I did not add references because there's probably like 30 papers in each of these categories. Okay, so let's go to task one, which is knowledge graph path queries. So I want to differentiate what we are doing with single hop inference, where you're given a single relation connecting an entity pair, like Melinda Gates and Gates Foundation, and you're inferring a missing link. And in multi-hop inference, there could be a path of any length connecting an entity pair, and you want to infer missing links here. Okay. So I'm going to motivate why deep neural networks are a good choice for this task by going over previous work, and I think the previous work here are basically symbolic systems that treat each path independently. Okay, and what happens when you treat each path independently is that there's a feature space explosion. So there's multiple ways to refer to the same relation. So when you're dealing with knowledge graph, it's also common to add triples from text. So these are OpenIE style triples. And then there's like many ways to refer to the same relation. So for chair of, you can also say it as heads, leads, leader of, and so on. And then there are many ways to, and then this means that there are many paths in the data set, and at test time, it's likely that you're going to be hit with unseen paths, okay? And models that treat each path independently cannot perform reasoning on these unseen paths. So as a solution to this problem, we developed this model that uses recurrent neural network. So the first step is to convert relations to some distributed vector representation. And then you run an RNN on this path. So the recurrent neural network builds up a vector representation for the whole path. And to perform reasoning, you represent the target relation, again with a vector representation. And then you're going to use the vector similarity to figure out whether this relation exists between these entity pair. Okay, and what this gives us is that now we can start generalizing to unseen paths, right? Even if the whole path is not seen during training, but if the individual relations are seen during training, this model can still construct vector representations for the whole path, and you can perform reasoning. Okay, and one detail that makes this task not that straightforward to apply RNNs is the fact that there is not one path connecting an entity pair. There is actually many paths connecting the entity pairs. Okay, and during training, we do not know which path is actually responsible for making a prediction. So this requires some kind of selection or attention mechanism. And the first time when we wrote this paper, the attention mechanism was not really popular. So our paper was, the first version of the paper came out simultaneously with the soft selection mechanism, the neural Turing machine, and memory networks work. So basically what we did was something very similar. We first construct vector representation for each path independently by running the RNN. And then you want to predict a target relation. So you compute similarity score for each path. And then we use a max function, basically saying that the path that has the highest score is what is responsible for making the prediction. Okay, and this was actually just motivated by computational needs. At that time, we didn't have GPUs at UMass. And so if you use the max function, you would need to backpropagate only to one path. And so that was our first crack at this task. And now we can train this model with backpropagation. Okay, so I'm going to show results. So this is, we constructed this massive data set that uses Freebase and OpenIE triples from ClueWeb. So it has like 190 million paths. So the first we compared with symbolic methods, and they perform reasonably well. And then our method, which is based on, which uses neural networks, performs almost as well as these symbolic methods. And yeah.
So explain to me what the test set looks like?
Sorry?
You construct the test set?
Yeah, sure. So the data set is basically, you're given, you want to predict missing relations. So you hold out 46 relations, for example, from Freebase. This was randomly chosen. And we collected paths connecting entity pairs that are present in this relation. So this is done by random walk algorithm. I used code from Matt Gardner. So I followed basically the same experimental setup as the path ranking algorithm work, where you're given a relation, and then you're given, let's say, like 100 positive entity pairs and 1,000 negative entity pairs. And during training, you know what the positive and the negative entity pairs. And at test time, you don't know whether they're positive or negative. And then the model has to rank the positive ones above the negative ones. Okay,
Do you train these jointly, or do you train for each path independently?
It's all trained jointly. So there's a single model for predicting all the relations. We also have results where we train for each relation independently, and that performs slightly worse because when you're training a single model for all the relations, you get information sharing, and the model overfits lesser, basically. Yeah.
And the minimum path length is 1, is this right?
Is 1, yeah. I mean, there's sometimes it's just a single hop prediction.
So do you have any characterization of whether the contribution is coming from the
Hmm.
multi-path or the
Yeah. Can I go to the next slide? And yeah, no, it's fine. I don't have exactly those numbers, but I'll make a comment on it. Yeah. I just want to finish this, and then finally, we also got GPUs in our lab, and we tried other attention procedures. So you can take the average score instead of just the maximum, or you can take the top k, and then finally log sum x with a continuous version of the max function. And once you do this, you start performing much better than the symbolic methods. And the intuition here on why max functions and functions like max work better than average is that for a single entity pair, there's like hundreds of paths connecting them. And if you use the average function, there's a lot of chances to overfit, right? Because there's many noisy paths. And if you let neural networks, if you give neural networks a lot of ways to overfit, they tend to overfit very, very quickly. So if you use a continuous version of the max function, we found that to work the best. Yeah.
Is log sum x just softmax?
No, it's you take the I forget the exact formula, but you take the you first exponentiate each score, and then normalize. I think there's a log somewhere. I forget, but it's basically you can think about it as the scores are basically it's like softmax with the temperature, so that it's very it's concentrated on the first few things in the set. Yeah.
What is the second line? That's tracking and doing plus parameter?
Yeah, definitely. So, I mean, the motivation for using these RNNs is to generalize to unseen paths, right? So for the symbolic systems, one way you can do that is you can create bigram features. So if you have a path, let's say A hyphen B hyphen C, you can create bigram features saying for A hyphen B and B hyphen C, similar to like how you create bigram features for sentences.
So you don't have to see the entire path, you only see
Yeah, but then it's harder to perform reasoning with that, right? Like this task, you actually need to understand the whole path to perform reasoning. So, I mean, that's why I think you don't get a boost by using bigram features. Yeah, sorry, yeah.
I assume this is the original PRA from Lau et al. Did you compare with like maths improvements?
Yeah, so I mean, I couldn't, or we couldn't run maths code on this larger data set because I think it takes a lot of time to. I've been talking with him. I don't know whether he tried, but there was definitely he published a paper after this one, but that uses basically it uses the vector similarity to basically, if you have an unseen path, you try to replace relations in that unseen path using vector similarity. But I don't think he was able to run his code on this data set, so because it takes a long time.
When do you get the training data?
Oh, so you take Freebase, and then for some, you're given positive facts, right? Like for some relation, you're given positive entity pairs, and then so you use that for training. And then negative evidence is basically.
How do you know which chain in the path corresponds to the right relation? So you say you're inferring relation going multi-hop.
Yeah.
Here. So when you build the trained data, how do you know which one of those relations is the right one?
You mean which one of the paths is the right
Yes.
one? We don't know. The model figures it out, right? We are not given that information.
So in your initial example, you know that where Melinda Gates lives. Melinda Gates lives. So
Yeah.
that's the label.
That's the labeled data. Yeah.
And,
And about the path length, basically what we found is if you restrict the path length to be very small, like 2 or 3, then the performance of the RNNs is similar to the symbolic systems. And this is because there are not many unseen paths at training, or there's not many unseen paths during test, right? Because if you restrict the path length, there are just like there's a smaller number of paths, and you see all of them during training. And then the absolute performance also drops. But as you increase the path length, you start seeing unseen paths during training, and that's when the RNN model starts performing better.
Does it make sense to compare this head-to-head with the universal schema?
Yeah, we have the numbers in the paper, and I don't remember it at the top of my head, but it performs, I think it performs something like, the performance is in the 50s. So because it's performing reasoning only on one hop as opposed to the whole path. Yeah, yeah. Okay, so here I want to show some eye candy. So these are paths that are predictive of the relation that the model has picked up. So the first half is paths that are seen during training. So these are paths that also the symbolic systems could have picked up because they can perform reasoning on these paths. But what is cool is that the model can also perform reasoning on these unseen paths, right? And this is for predicting the relation place of birth between entities A and B. Okay. And finally, I want to talk about one more small experiment that we ran. This is where we can perform zero-shot prediction. So the model has to have a vector representation for the target relation, but you don't need to explicitly train for that relation. So even if that relation occurs in the path, you still have, so the model would have still learned a vector representation for that relation, and you can use that to make predictions, right? And that's kind of cool. You cannot do that, I think, with like methods like PRA. And here you have only a random baseline because you don't have any supervised information for that particular task. And we can, I mean, our model performs much better than random baseline. But again, if you have supervised information just for that target relation, and if you explicitly train for it, it performs much better. Okay.
So the criteria here is that we're only looking at relations, where, or the entity pair doesn't have another path to go around. Is that right? Because if you have it in the training data, the relation exists in the training data, maybe there's another path, even if you don't use it, but then the setup would not be very
I actually don't get the question. So, so there's a path between the entity pair and.
The relation exists while you're training, which is what you're assuming, so that you can learn for it. Then why are we assuming that there's no other path between the two entities?
Oh no, what I meant is that relation, we are not explicitly training to predict that relation.
But you could have.
You could have. It's just like it's just like a small experiment where we wanted to observe whether the model can, make these zero-shot predictions. So I mean, in a case like, let's say, you want to make predictions for all of freebase, which I think thousands of relation types. Maybe you don't want to train on each relation explicitly. Maybe there's a way to get juice from here, or if you add a new relation type to the knowledge graph, and now we can start generalizing to that. Yeah.
Thanks. If you had extra information like taxonomy over entities or
Uh-huh.
maybe some rules that connect different relations, is there a way to incorporate it?
Yeah. So I didn't talk about it here, but basically we also have a model where we where we construct a vector representation for the entities, and that comes as like an average of the types that entity participates in, and we get like a 5-point boost by using that. But I didn't talk about it just for lack of time, but we can chat about it later. Yeah. Okay, so this is all I have to say for task 1, which is basically performing simple reasoning, but on a massive structured knowledge graph. Okay, so now I want to move on to task 2, which is to do program induction or semantic parsing with neural networks. So to refresh your memories, you have semi-structured tables, and then we use this data set from the Stanford NLP group. And there are basically two kinds of question. So one is the lookup question, for which the answer is an entry in the table or a set of entries in the table. Okay? And there is number question where the model has to generate a number. So this is like something like how many games were telecasted in CBS, and you need to first match the entry CBS and then do a count operation on it. Okay? So basically, you have an input natural language question, and you need to convert to this program. So the challenge here is, the first challenge here is there's like multi-step reasoning. So a program is a sequence of function calls. So the model has to figure this out and has to figure out the correct arguments to these functions. And a bigger challenge is that you're given only weak supervision signal. So what that means is that you're given the question and the table and only the final answer. So the program, the intermediate program is latent. Okay, and if you think about previous work in semantic parsing, when we wrote the first paper, I think either the models required strong supervision, which is you require question and program annotations, or when you have weak supervision signals, there's some kind of rules to guide the program search. Okay, and we wanted to develop like end-to-end neural network models for this task, and it's not really it was not really clear how to do that, right? Because learning discrete functions with neural networks is very challenging. So this is one paper that basically shows how adding two n-bit binary numbers with neural networks is hard. And if you think about the task we are dealing with, you need to do like addition and all these discrete functions on tables of containing like hundreds or thousands of rows. Okay, so as a solution to this problem, we developed this model which we call neural programmer, which is basically a neural network with a set of built-in discrete operations, and these operations are defined to the model, and the model basically takes in an input question and also a table, and the model has to use these functions to perform reasoning on this table, right? And at a very high level, how that happens is the model runs for some fixed number of time steps, and at each time step, it selects a function, and it selects an argument to this function. And once you keep going for some number of time steps, you get a program. Okay, and basically, as shown here, the data flows in from the table to the function, and the function is executed. Okay, and those three variables, I'm not going to explain right now in detail, but you can think about it as like maintaining state over programs. Okay, when the program is built up, these are like variables where the intermediate outputs are stored. Okay, now I'm going to zoom into the neural network part. So in the simplest case, you can think about it as you get a natural language question. You run an RNN on it to convert the question to a distributed vector. So this, in the simplest case, again, it's the last hidden state of the RNN. Okay, and then there's an input table which contains columns, and then there's a set of built-in operations. The model has to select a column, which is the argument, and it also has to select a function. Okay, and how it does it is basically you first convert the column names again into distributed vectors, and then there are you represent the functions also as distributed vectors, and the model does a selection procedure. Okay, so to select a function and a column, the model needs to know two things. The first is it has to know what the question is. The second step is the model has to know the program it has built up so far. Okay, so this is taken care of by the history RNN, which basically keeps track of the program it has built up so far. Now, using these two vector representation, you perform the selection operation. Okay, and I'm going to explain the selection operation in more detail in the next slide or the slide after that. Okay, but this is just, sorry.
So the phone selector, it's not clear to me what you have
Yeah, so you can think about it as like the column selector. You take these two vector representations, Q and HT, and then you run a single feed forward layer to get a vector to get a new vector, which I call the column selector. And then the column selector is used to induce a softmax over the column names, right?
Assume that all the tables in the training set have the same set of columns?
No, because the column names are, again, like those are words, right? And you can run an RNN on the column name. You can run the same RNN on the column name to get vectors for the for column names.
So the softmax is over the current table that we're working with?
Yeah. For each question, you're given a table that on which you have to perform reasoning. Yeah.
Can you say a bit about the space of functions you can represent by this alternating column and operator selection?
I mean, in the actual detail, we actually do more than just the column. So it's if a function requires more than one argument, how I've defined, there's multiple ways to define it, and how I've defined it is that it happens over 2 time steps. So it selects one argument in time step 1, and then selects another argument in time step 2, and then it's chained together. So operations like AND and OR, for example.
So that is way more powerful than what you're...
Yeah, and I just didn't go into the details. And for the wiki tables data set, I don't think there are functions that require 2 arguments. So I had a paper before this on the synthetic data where there were questions that involved logical AND and logical OR, for which there were 2 arguments. And then there was like a difference operation which required 2 arguments. And I had implemented it as like running for 2 time steps. But yeah, you can do that step in multiple ways. Okay. So yeah, so to basically, the history RNN keeps track of the program it has built up so far. And that's basically done using, by passing the function and the column that the model has picked at the current time step, right? And then this is the story I've already told. You run the function on the input argument, you get an output. And the final output of the model is the output at the last time step. Okay. So now I'm going to, yeah.
Do you know when to stop?
Right now it's run for a maximum number of time steps, and then there's a no op. So it can basically induce programs up to length capital T, for example. And this is to make it differentiable. And now I'm running experiments where you can have a discrete neuron that says whether you want to continue or not. I don't have results yet. Yeah. But it's hard to, I'm going to say just one thing. It's hard to make policy gradient work in this setting because it's hard to define a good reward function because you're dealing with numbers, and which means that even if you normalize, you could actually be going to a better program, but the reward could be lesser, right? Like because it's sensitive to the numbers in the table, and policy gradient is extremely sensitive to the how you've defined your reward function. And what happens is that it doesn't converge at all, or it converges to some extremely bad saddle point or minima, and it's super hard to train policy gradient in this setting. Yeah, but it's with initial experiments. This is what I've observed. Yeah. So for the wiki tables data set, as I told you before, there were 3 variables: row selector, which basically these are functions that whose output is in the size equal to the number of rows. So these basically, the row selector keeps track of the rows that are active, and these functions would become more clear as I start giving you examples. And then the scalar answer is basically stores output for number questions, and then the lookup answer stores output for lookup questions. So the lookup answer basically is a matrix in the same dimension as table, and each entry is a probability that that entry is part of the final answer. Okay. Yeah.
The output of the row selector needs to be a discrete which is basically all of the possible subsets of rows. Is that right?
It's a binary saying whether that row is active or not. So if you have a column with numbers, and let's say the question is like, what are the how many teams have scored at least 5 medals? So you apply something like the greater than 5 operation on a particular column, and so that's going to return a Boolean.
So that,
Yeah.
this vector binary will specify all the subsets. And
Oh, I see. Yeah.
but how do you? So it's like, how do you represent this? How do you make this prediction?
So these functions are defined, right? Like the model is not learning to how to perform the gradient operation. So the model just calls this function.
I guess another way of asking, are these functions decomposable to, can you independently evaluate each row, or is it a function of the subset?
I don't understand what do you exactly mean by independently execute each row.
If you have to evaluate and figure out all possible subsets as well as the same, then it's a very tough function to find.
I see.
And
All
the
possible.
examples you gave is all teams that are, then you can independently say yes, no for each row.
I
That's
see.
a simple function.
I mean, again, you can since the model is not learning these functions, you can define whatever function you want, right? And the model is basically does not even look at the output of the function. It just looks at the question and the table to build the program. And the functions are defined by us, so you can potentially define any function. So to make things more concrete, I'll go over an example. So you're given a question like, what was the total number of goals scored in 2005? So this is a question that requires a program of size 2 to be induced. So this is one way that the model can answer this question. So for the first 2 steps, it picks a no op. Basically, it does nothing. And then it performs a select function on the column season. So this basically selects 2005. And then in step 4, it calls the print function on the goals column. Okay, and so this is a way that the model can answer this question. But yeah.
How do you pass the 2005 to the select season?
So you can do it in multiple ways, but here we basically use an exact match operation. So for each entry in the table, if that phrase exactly matches some phrase in the question, we return 1. Otherwise, it's 0. So select function is defined by us. But a more general way would be to use word vectors, right, to do the match. But we found that you start overfitting a lot. Like again, like this is a data set with 10,000 examples. So if you start using distributed vectors to perform this match.
In the select season, you basically take the season column, then match all the words with all the words in the question.
Yeah.
Then you find the match and say these are the ones.
Yeah, basically for each entry, you in that column, you perform a match with the question.
With
Yeah.
all the words in the question.
Yeah.
So it's an exact match now.
Yeah. So this. Yeah.
Okay.
This is what they did in the baseline. So yeah. So during training, you're not given this program, and you're given only the final answer. So this is a setting where I think it's very natural to apply something like reinforcement learning, right? You're given some input, you have to perform some number of steps, and then you get a reward in the end. But it's hard to make reinforcement learning work, especially when you have small number of examples. And I think the crucial trick that I think helped us get good results in this data set is that you can actually train this model just with gradient descent. And how we do it is you can think about it as each function in your model, each function that's provided to the model gives some output, and then the model gives you a probability distribution over this function, and then you take a weighted average. So basically, when you're doing reinforcement learning, you're sampling from the softmax, and here you're taking like a mean field, basically taking a weighted average of the outputs, right? So to make this more clear, let's say you have 2 functions and 2 columns, and these are the output of applying operation on a column, and the model gives you two two softmax distributions, one over the functions and one over the columns. And the final output is basically the weighted average. Okay. So this is basically a case when the function is returning you a scalar. But we have functions that return symbols and vectors. But the good thing with neural nets is that symbols are just vector of numbers, right? So you can still take did I press something? Okay. The good thing with neural networks is that the symbols are just vector of numbers. And what we actually do is you can take weighted average of functions that return the same data type. And all you need to do is keep track of variables that have a particular data type. So you have functions that return a vector of, say, the size of number of rows. You take a weighted average only among those set of functions. And then you take a weighted average among functions that return numbers. Yeah. Sorry, I didn't explain that properly. I'll try it once more. So here I showed basically functions that return numbers, and you can take a weighted average. But in this data set and in general, you want to handle functions that can return any data type, right? And all you need to do is you need to basically store all functions that return a particular data type, and you take a weighted average of those outputs. Okay, and using this trick, now you can train this model just with gradient descent. Yeah.
I'm slightly confused because we were talking about column-based operations the slide before, and now we're talking about number returning operations. I'm like, which ones? Are we talking about numbers or about columns of numbers?
There are the columns could be numbers or.
The operation is a select. So it
Yeah.
does 5 ones.
Yeah. There could be both. So the table could have columns that have numbers. There could be tables that have whose columns have words, right? And you basically sorry. So something like the select operation can run on both columns that have numbers and can run on columns that have phrases, right? Yeah.
I think the picture is slightly
Uh-huh.
confusing because
Yeah.
the picture confuses just one number. The dimension of the thing is 1 versus the dimension column is n.
So
Basically, in that for every n or
so you basically have a variable for every data type. So for all functions that return a vector with size equal to number of rows, you have a separate variable, the row selector, that's basically going to aggregate outputs from functions that return that data type. And so there's a variable scalar answer that basically stores the aggregate of functions that return a number. Right. So you don't need to mix them both. Like you have separate variables for them. Yeah.
So is your reward just binary, like 1 if it returns the right answer? And 0
Yeah, that's actually the next slide. So the training objective is, so that's a non-differentiable loss function, but and it's also not very informative, right? Because there's thousands of programs, and the chances of getting a positive reward is very small. So what we do is basically the model has to again either output a number or a lookup, right? And for number answers, we use the square loss after normalizing the numbers. And then for lookup question, the model basically gives a probability that a particular entry in the table is part of the final answer. So you can compute the log loss for each entry, and then you take an average of that log loss. So this is the training objective.
So you're still using policy gradient, but the reward is?
Sorry, we're not using policy gradient. We're just using gradient descent. So the goal of using this soft selection procedure is that you can now backpropagate just like normal, because taking a weighted average is a differentiable function, right? You're not sampling from the softmax at all. And that's basically why I think this method works well. Yeah.
You see that after training for
Yeah, it's a good question. So it doesn't get as sharp as you want in the end, even in the end. But and I'm going to talk about it a little later. But at test time, you don't need to take a weighted average, right? Like you're doing the weighted average trick so that you can backprop during training. But at test time, you can just do hard selection, and that way, all the model has to do is to put the probability mass on the correct function.
And does it work better this way?
It works much better because again, like the answers are like numbers, and then they're very sensitive to the scale of the softmax, right? Like if it's 0.9 the correct program, it's actually you get 0 points, right? Because you need to exactly match the answer. Yeah. Okay. So the training objective, I described that. And one other detail that makes this challenging is that the answer is simply written down. So which means that that's going to introduce some ambiguity, right? Like, so let's say you're given a question and the answer is a number, and that number also appears in the table. Okay. So now you do not know whether you want to generate that number or you want to look it up. And this information is not given during training. And what we do is basically we compute the loss for all these different paths, basically these different programs, and then pick the one that gives us the least loss. And what we are intuitively saying to the model is that you need to get to the final answer somehow, and it doesn't matter what the path is, right? Because during training, we're not given that path. Okay, so when our work was submitted, there was also other neural network-based program induction systems that were released, I think, concurrently or shortly after. So I think there was a lot of work on like methods that use the strong supervision signal. So here you're given the question in the program. And then the work that is most similar to us is the dynamic neural module network. And there, I mean, one way to think about it is that instead of using the weighted average trick, they sample from the softmax and train the model with reinforce. Okay, and what happens then is that they actually, I think, run on a simpler semantic parsing data set, and even on that, they have to basically convert the question to its dependency parse, and then they consider only the top 10 programs. Okay, and so basically, the neural network is searching only over a small set of programs instead of the whole set of programs, right? So there are components in that system that are not really optimized for the task in hand.
By the way, there's
Yeah.
an end-to-end differentiable version of it.
Yeah.
So
Yeah.
learning to reason.
Yeah. So I mean, but still, it's the end-to-end learning is still not really done on the. They've not really tested on the wiki tables task, and that's one of the reasons for that is the operations that are built into neural programmer. In the neural module network, those are also neural networks that are learned for the task, right? And then, as I discussed before, those functions have to be discrete, which means that it's hard to train those, like the function neural network. Like it's hard to train the function neural network, for example, to add numbers in the table. So it's like solving kind of like a different kind of a problem where, let's say, you want to do question answering on images, and where the sub-functions have to do some kind of image processing. And for that, probably using neural networks are a good idea. But in this setting where you want to manipulate things in a table, and then there's a lot of discrete functions involved, I think this is a better idea. Okay, so I'm going to go into experiments. So these are experiments on the wiki tables questions data set. And one more challenge is that the databases at test time are unseen during training. So here the model does not have a fixed schema that it can map to. So it has, given the context of a question, it has to understand the column names and induce the correct program. And as I told you before, we use hard selection at test time. So we ran like existing neural network models like seek-to-seek and pointer networks, and basically they take in the question and the table. So it's a big input, and you cannot basically feed in big tables, right? Like you cannot process them. So I considered only tables that are like have less than 10 rows or something. And even with that, it's basically really hard to get these models off the ground. And I think this is basically because learning discrete functions is I think, really hard.
The output sequence is a sequence of selections for operations and column?
So you're not given that during training, right? So the output is just the answer. Yeah, so it's just, yeah, so it's a really hard problem for neural networks. So these are results from the paper where they created the data set. And I think, yeah, the state-of-the-art semantic parser, I think this is still the state-of-the-art, is 37%. Luke was telling me there's a recent paper from Jayant and Matt Gardner that are beating the numbers, but I've not seen it. And so this is neural programmer without dropout and weight decay, and that gets 30%. And basically, since the data set is extremely small, we had to add all kinds of regularization, and everything helps, basically. And we were able to get something like 34%. And then finally, by ensembling 15 models, we were able to match the performance of the semantic parser. So I mean, these results are still very surprising to me, because this is only 10,000 examples of training. So if you think about other reasoning applications, and the neural network models start performing really well only if you have at least an order of magnitude more data. And I think this is likely to happen here too, because the accuracy of this model on the training set is 20 or 25 points higher than in the dev set. So there's significant overfitting happening even now. Okay. Finally, this was a pleasing result that came out, I think, a few weeks back, where Mohit Iyer and his collaborators basically created a new data set for conversational question answering. And they ran both the semantic parser from ICE and PERSI, and also the neural programmer model. And without any hyperparameter tuning and anything, they were able to beat the traditional semantic parser, which was very good. And I think the state-of-the-art results on this data set were an extension of neural programmer to the sequential question answering setting. Okay, so yeah.
What does work better in this problem than you produced?
I've not. It basically came out only a few weeks back, so I've not fully read it. But I know that they got this result because he was emailing me about using the code. So I think it came out a week or two back. Yeah. Okay, so how much time do I have left? Do you know? Or 10 minutes? Or,
5 minutes,
okay.
including questions.
Oh, okay. So these are some example programs that the model induces on the dev set, and basically I'm showing. So if it's a dash, it basically means a no-op. Okay, and these are questions for which the final answer is a number. Okay, and these are questions, some examples of questions where the final answer is a lookup, and the last question is kind of like one of the more complicated questions where you need a program of length 3. So who had more silver medals, Cuba or Brazil? So it's in step 2, it selects the nation. So that basically makes the row Cuba and Brazil active, and then it performs an argmax on the silver column, and then finally it performs a print going back to the nation column. Okay. And then in this slide, I wanted to show examples where the program is not perfectly correct, but it still gets the correct answer. Okay. So these are, if you look at the first question, who was the next appointed director after Lee P. Brown? It selects the name column, and then it performs a next, which is correct. And then it calls a last function, which basically the last function among the set of active rows only picks the last one, which is not required for this question. But I think since during training there's these examples, there's only one entry matching in the table, this would give you the correct answer. So this is like one drawback of using weakly supervised examples, right? Like you can get away with inducing I mean, here it's at least partially correct. In some cases, you can get away with inducing wrong programs that give you the correct answer. Okay, so basically we started with neural networks for knowledge representation and reasoning, and we went through simple reasoning for knowledge graph path queries and program induction for semi-structured web tables. And if you take a step back and look at what was actually required, is basically only 3 things. So whenever you have sequences, you use RNNs, and there is some attention or selection mechanism that is differentiable, and then you train the model with backprop. And using basically these 3 components, we were able to get really good, I think really good results on 2 good data sets. And the code and data for all these experiments are available. And I'm going to very briefly describe future research directions. I mean, I'm going to continue. I'm very interested in program induction, but I also want to just open up other things that I'm interested in. And these are a little high level and vague right now. So one is a lot of the focus was on when you're given a knowledge base, how are you going to represent and do reasoning on it? And I think it will also be interesting to think about whether we can acquire knowledge using these neural network models. So one example is the recurrent entity network, which is a recent paper from Facebook that basically uses end-to-end memory networks and treats each slot in a memory network as an entity. Okay, and it learns these entities end-to-end for a question answering task. And we've been trying ideas where instead of just having a flat memory structure, you also have relations connecting these memory slots. Okay, so you can think about it as like you're inducing these latent knowledge graphs for question answering. And I think this is really useful implications in tasks like building a model of the world, and also this recent work on transfer learning, where they showed that if you want to do image categorization, if you go through a knowledge graph, you can start categorizing using very small number of examples. And we've basically been getting good results with this model on the baby task right now, where we've been able to beat the recurrent entity network, and right now we are trying on more real world data sets. And then the second direction I've been thinking about is large scale generation. So right now we have models that can generate single sentences or like an image. And let's say you want to generate blogs or publications. And for this, you need models that are thinking at multiple levels of abstraction. And what I mean by that is that let's say you want to generate a publication, okay? And the generative model could be something like there's a master network that reads the title and sends a message to downstream workers that are running in parallel, okay? And then there's a separate worker for generating an abstract. There's another worker for generating the first 2 paragraphs of an introduction and so on. And then after generating every t time steps, these workers send a message back to the master. And now the master processes the information and sends a message back again. So these messages are basically distributed vectors. And now the hope is that because they're now running in parallel, you can perform large scale generation. And this is basically inspired from this very cool paper called feudal reinforcement learning, where they do something like this for RL. Okay, I'll stop now. I have one more idea, but I don't think I'll go over it. Yeah, cool. Thanks.